Good morning and welcome to the next class of this video course on advanced hydrology. In the last class, we looked at the various parameters of the Green-Empt infiltration equation. Then we looked at a two-layer model in which we can apply the Green-Empt infiltration equations when we have more than one soil type in the ground. Then we looked at the concept of ponding time. We found out how we can determine or estimate the ponding time using a certain procedure. Then we looked at the method to determine or to calculate infiltration after the ponding time. Okay. What we are going to do today is look at a few examples on whatever we have done in this course till today or till the last class. Okay. So, I would like to get started with the first example today. I would like to draw your attention here. So, what I will do is I will just write the problem first, then look at what the data are given, and then try to solve that problem. Okay. So, the first question or example problem we will take goes like this. Using the hydrologic model system concept, derive the transformation equation of differential transfer function. Which is this omega we had defined for a non-linear. Remember earlier we had seen an example of a linear reservoir. So, today we will look at a non-linear reservoir of second order. That is, your storage in the catchment can be represented using this equation K1 Q squared plus K2 Q plus K3. Okay. So, this is the problem in which we have to determine the expression for the transfer function operator for a catchment such that the catchment is simulated using a concept of non-linear reservoir, in which the storage is a function of or non-linear function of outflow Q, and which is given by the second order polynomial like this. Okay. How do we solve this problem? Well, we will follow exactly the same procedure which we did earlier. All right. So, what we will do is we will use the continuity equation and then replace the ds by dt term using the expression which is given to us. Okay. So, let us see how we are going to look at that. Using the continuity equation, we have ds over dt is equal to I minus q. This is the basic continuity equation we have derived. Okay. So, this first problem is basically coming from our first few lectures or the first chapter of your Venti-Chow's book. Now, we have the functions for the storage of the catchment. What we want to do is determine the first derivative of this storage function, all right, as a function of time, and then put that value into this equation. Okay. So, if we do that, let us first find out what will be the ds over dt. All right. As you can see that K1, K2, K3 are the constants, and the only thing that varies with the time is the either the storage or the outflow. Okay. So, it will be twice of K1 Q times dq over dt. Okay. All right. Q square as a function of time would be twice q dq over dt, because q is a function of time, plus. So, this was for this part, okay, And the second part, what will be the first derivative of this? It will be simply K2 outside and dq by dt plus what is the derivative of this term K3? K3 is constant, so it will vanish. So, you have 0. Okay. So, now what we do is we replace this quantity or put the value of this in our continuity equation. Okay. So, let us do that. What I will have is I minus q, let us say I put on the left hand side, is equal to this whole thing, okay, which is twice of your K1q dq over dt plus K2 dq over dt. Okay. Now, take the q on the other side, so that I is on the left hand side and outflow is on the right hand side. Okay. So, you will have twice K1 q dq over dt plus K2 dq over dt plus q. Okay. So, the q has come on the right hand side. Now, like we did earlier, let d over dt be represented by some operator d. Okay. Once we use this concept, we can write this equation as I is equal to twice K1 q d. d over dt is d and we are applying it to the outflow q. So, that will be taken out outside, and then you have second term is K2 d, all right, and it is being applied on q. Is this clear? So, what we have is this twice K1 q dq over dt, all right. This term corresponds to the first term, that is twice K1 q d, and the second one, this one corresponds to this term, okay, K2 d operated on q plus q, all right. With this, what you should be able to write then is the outflow from your system model as a function or operator applied on the input. Okay. And this whole operator is applied on I, okay, and this, as we know, we represent this as omega times I. Okay. So, that gives you the formation or the representation of omega as this expression twice K1 q d plus K2 d plus 1. Okay. So, this is your transfer function operator for a catchment when we assume the catchment to be a non-linear reservoir of second order. Okay. Now, you can see that you can extend this concept, all right. We can have any form of complex system. We can try to simulate our catchment using more complex geometry, so that we are able to model the complexity in the which are involved in the rainfall runoff process or the catchment processes. Okay. So, this was the first example. Now, what we are going to do is look at another example, and this will involve the subsurface hydrology chapter, use of the infiltration equations. Okay. So, looking at the first one, second example, the first one from the subsurface chapter. First, I am going to write it down slowly, so that you can understand this. The lab experiments were conducted to find out or to determine the hydraulic conductivity K of a certain type of soil. Okay. How it was done? Well, first a tube of cross sectional area square centimeters was filled with the soil. And laid horizontally. The open end of the tube was saturated, or some water was applied, and after 15 minutes it was observed that it was observed that 100 centimeter cube of water infiltrated into the tube. I am sure some of you may be getting the idea already how we are going to solve this problem. Okay. If not, we will see in a minute. The tube was then laid vertically, and the upper end was saturated. Okay. So that the water will travel in the vertical direction now, and the amount of water infiltrated was measured. It was noticed that a total of 3.74 centimeter of water infiltrated into the tube in half hour. So, using this data, your first task is to determine the hydraulic conductivity of the soil. Okay. So, this is the first part of this problem. It is a long statement. I will quickly go over it again. The laboratory experiments were conducted to find out the hydraulic conductivity of a certain type of soil. First, the tube was laid horizontally, okay, and some water was applied on one side, and the amount of water that infiltrated into that tube was measured, okay, and that information is given to us. Okay. Then what was done? The same sample was dried, and then it was placed vertically, okay, in the vertical direction, and it was saturated from the top, and the amount of water that gets infiltrated in the vertical direction, that was measured, and all of that data is given to us. Okay. using these two information or these two data, we have to find out the hydraulic conductivity. All right. Once we have done that, there is another part of this problem. A small garden, okay, it may be in your hostel or in your home outside, of area 0.01 hectare, which consists of the above soil, consisting of the above soil means what? Means it has the same properties, soil properties, okay, is subjected to a rainfall intensity of 5 centimeter per hour. And what we have to do in this part is compute the ponding time, and the amount of water infiltrated at ponding, okay, that is just at the ponding time into the garden. Assume the effective porosity as 0.486, the suction head as 16.7 centimeters, and the initial effective saturation, which as you know is denoted as SE, as 30% when the rainfall started. Okay. So, this is the problem statement, which is quite long, but it is important to understand. Okay. So, you take a sample which is cylindrical in shape, all right, we lay it first horizontally, do certain measurements, then we lay it vertically, measure the water that is infiltrated, then we need to determine what is the hydraulic conductivity, and then we say that we consider a problem of rainfall event into a garden, all right, and then some of the data that are given to us, we have to find what will be the ponding time of the garden, the rate of rainfall is given to us, and we have to find how much water will infiltrate into the garden at the time of ponding. Okay. So, it should be very easy to see that which equation we are going to use here. Okay. Because the sample is laid horizontally as well as vertically, we will use the Phillips equation, because that is the equation we had seen which allows us to use or compute infiltration in the horizontal direction, and also it is applicable for the vertical direction. All right. So, let us look at the solution of this problem. Okay. So, what we are going to do is, first thing is just list out all the data that are given to us. Okay. So, first I will write down or compile all the data. The cross sectional area of your soil sample is 40 square centimeters. In the first case, two data are given. First one is that 100 centimeter cube of water infiltrates for the horizontal case, okay, in 15 minutes. Okay. For the second case, 3.74 centimeter of water infiltrates for the vertical case, and that happens in half an hour. Okay. Also given to us is the area of the garden. I will use the subscript as G here to distinguish it from the other area. this is given to us as 0.01 hectare. The rainfall intensity is given. This is for the second case, I as 5 centimeters per hour. Okay. We have to find what is K, what is the time to ponding, and what is the amount of water that is infiltrated at ponding, that is Fp. Okay. The other data that are given to us is the effective porosity. What is effective porosity? It is theta E, which is eta minus theta r, is given to us as 486. The suction head psi is 16.7 centimeters, and the initial effective saturation of the soil, which is denoted by SE, is given to us as 30%, or as a fraction we say that it is 0.30. Okay. So, as I said, we will use the Phillips equation with all this data that are given to us. Okay. So, first we will look at the horizontal case. Okay. Using the Phillips equation. Okay. For the horizontal case, what we have is F is equal to nothing but S T half. Okay. Now, in this equation, what are the knowns and what are the unknowns? You can see that in this equation we know the time, all right, and we also know F, how much water gets infiltrated. So, basically the first data point can be used to determine the value of S or the sorptivity, all right. So, if we did that using the data for the horizontal case, we know what is F of T. It is nothing but 100 centimeter cube of water infiltrates, and we divide it by this cross sectional area of the sample, so that we have the infiltrated water in the length units. So, it will be 2.5 centimeters at t is equal to 15 minutes, and let us convert everything into hours. So, 15 minutes will be 0.25 hours. Okay. So, we put these values, and let me say that this is my equation number 1. All right. So, I put the value of F and T in equation 1. Okay. If you do that, you will have 2.5 is equal to S times time is 0.25 raised to the power half. Okay. So, that will give you, should be easy to see that you can calculate the value of S as 5.0, and its units will be centimeter hour minus half, okay, as per this equation. All right. Some of you may find this into some other units. So, I will just give you the answer. It will be 0.645 centimeters minute minus half, or 8.33 times 10 minus 4 meter second minus half. So, we can represent the answer in any units we want. So, I am giving you all these numbers so that you can verify these. Okay. So, for the horizontal case, we have determined the value of S. Okay. Now, what we do is we apply the same Phillips equation for the vertical case, all right, in which the gravity forces will be predominant or will be important, and the K term will appear, and that is where we can find out the value of K or the hydraulic conductivity. Okay. If we do that, we would have, or let us first write the data. Vertical case, the data that are given to us is that F of T is equal to 3.74 centimeters. it is already given in length units. So, we do not need to convert it, and this is at t is equal to 30 minutes, which is 0.5 hours. Okay. So, what you do is the Phillips equation for the vertical case has this form in which both suction forces and the gravity forces are important. Okay. So, now we put the value of S, we know the value of T, and we also know F. The only thing that is unknown is K, which we can find out. Okay. So, if you put the values, what you will have is 3.74, S is 5, the time for the vertical case is half an hour. So, under root of 0.5 plus K times 0.50. Okay. You can solve this. I am not going to go through the steps, just give you the value of K, that will be 0.41 centimeters per hour, or it will be 6.82 times 10 minus 3 centimeters per minute, or it will be 1.14 times 10 to the power minus 6 meters per second. Any of these three answers is fine. Okay. So, this is your answer to the first part, in which we found out the value of the hydraulic conductivity using the lab experiments or the observations which we made using the horizontal and vertical cases. Okay. Now, we go to the second part of this problem, in which we need to find out what will be the ponding time and the cumulative infiltration at ponding. Okay. That should be fairly easy to see. We had derived the expression for the ponding time using Green-Ampt equations, and it was given by this K psi delta theta over I times I minus K. Okay. So, on the right hand side you see the K we have just found out, psi is given to us, the rainfall intensity is known, K we have just found out, and we just need to evaluate what is delta theta. Okay. What is delta theta is? It is a measure of initial conditions, or initially how much is the saturation or how much is the moisture content. Okay. If we go back to your notes, you can see that this delta theta is given by this expression. Okay. We had derived this while looking at the effective saturation for the Green-Ampt equation, different parameters. All right. The effective initial effective saturation is given, the effective porosity is also given. So, we just put these values, so that it will be 1 minus SE is 30%. So, it is 0.3 times effective porosity is 0.486. So, that would tell you that delta theta is 0.3402. Okay. Put all these values into your expression for TP, and we should be able to find out what will be the time to ponding. So, if you did that, you will have TP, K is 0.41 times psi is 16.7 times 0.3402 is delta theta, and everything divided by I is 5 times 5 minus 0.41. Okay. One thing I would like to caution all of you is that whatever expression we use, we should be consistent with the use of our units. All right. Rainfall, infiltration, the parameters phi, etc. We should make sure that we are using in the same units. It is not that one thing you use in centimeters per hour, other thing you use in meters or in seconds. All right. So, everything should be consistent, so that the units would cancel out and the final answer will be in hours or seconds or whatever you are using. Okay. So, you can notice that this aspect has been taken care of. So, this answer would be in what units? hours, 1015 hours. Okay. Then you can convert it into minutes if that is desired. So, that your T_p would be equal to 0.1015 hours, or it will be about 6.1 minutes. So, what does that tell us? That it will take about only 6 minutes for water to start ponding in that garden once the rainfall starts at that particular rate. Okay. So, that is the first part of the second component of this problem, and then we just need to find out what will be the infiltration, amount of water that infiltrates. Cumulative infiltration just at ponding, as you know, is nothing but I times T_p, okay, because before the ponding there is not enough supply of water available. All right. So, whatever water falls on the ground or on the garden, everything will get infiltrated. So, I is the infiltration times the time to ponding. Okay. So, you can find out it will be 5 centimeters per hour times 0.1015 hours is what we just found out. So, that it will be 0.5075 centimeters. Okay. You can convert it into other suitable units. So, it will be 5075 centimeters multiplied by 1 over 100 centimeters per meter times the area of the garden is 0.1 hectares. You can convert the hectares into square meters. So, that is 10 to the power 4 square meters per hectare, and then if you want you can convert it, this is in meter cube, all of this you can convert it into liters. So, you have 1000 liters in 1 meter cube. Okay. So, you can see all the things will cancel out, and what you will have is the answer in liters, 507.5 liters of water will infiltrate at t is equal to 6.1 minutes. Okay. So, your final answer then is Fp is equal to 0.5075 centimeters or approximately 508 liters. Okay. So, that is your final answer as far as the cumulative infiltration is concerned. All right. So, you see that we can solve some practical problems using some of the equations or some of the methods we have seen for infiltration. Okay. So, this was the example of Phillips equation, and the next example which I would like to take would be on the use of Green-Ampt equation. Remember, we had said that the Green-Ampt equation is a little complicated as far as the solution is concerned. Why? Because it is non-linear in nature and also it is implicit. So, when we have any implicit equation, we do not have the expression to calculate our desired variable explicitly. So, we need to do some trial and error or some manual trial. So, I would like to demonstrate how we do that by taking one example on the Green-Ampt equation. So, if we see that, what we have is this example. So, this is my third example today. That is all we will do. It is on the Green-Ampt equation. Or the use of the Green-Ampt equation. Okay. First, I will state the problem like I did for the previous two examples. Use the Green-Ampt method to evaluate infiltration rate which is F and cumulative infiltration depth cumulative infiltration depth, which is capital F, for silty clay type of soil, okay, at 0.1 hour increments, that is at every 0.1 hour, all right, up to 6 hours, okay, from the beginning of infiltration or your rainfall period. Assume the initial effective saturation, which is SE, as you know, as 20%, and the conditions of continuous ponding. This is important because we had said that all these infiltration equations give us the potential infiltration, or they assume the continuous ponding. So, if we have sufficient amount of water available, that is ponded depth is there, whatever we calculate from Green-Empt equation will be equal to the actual infiltration, all right. So, under this assumption, what we need to do in this problem is calculate the small f and capital F at 0.1 hour interval up to 6 hours. Okay. Obviously, we will not have time to do that, but what I would like to demonstrate is carry out the iterations for one time step, that is 0.1 hour. Okay. So, let us see what will be involved in this. Okay. And once we understand that, you can write a small computer program or you can use Excel to compute this or to complete this problem. Okay. So, what we do is, first of all, we need to find out the data, all right, what are the Green-Empt parameters. So, to be able to use any model or any equation, we need to estimate the values of the parameters of that equation. Okay. For the Green-Empt equation, there is a table in the book, this is 3.12.1. Okay. We can read out the parameters for silty clay type of soil, all right. So, I will just give you this data directly, so you can read it from this table in the Venti-Chau's book. So, it will be effective porosity is 423, the suction head for this soil is 29.22 centimeters, the hydraulic conductivity K is 0.05 centimeters per hour. What is the other data that are given to us is the initial effective saturation SE as 20%. So, as a fraction it will be 0.2, so that we can calculate the initial conditions delta theta like we did in the last problem. So, it will be 1 minus SE times theta E. Okay. This is given, theta is for that soil we have just written down, all right. So, it will be equal to 1 minus 0.2 times 0.423. Okay. That will give us delta theta is equal to 0.3384. Okay. So, this is we have determined the delta theta. So, once we have done that, we can find out what is psi delta theta. Remember, in the Green-Empt equation, psi delta theta is a common expression, all right, in the natural log inside. So, we can find out what will be psi delta theta. Psi is given to us as 29.22 centimeters multiplied by delta theta is a fraction 0.3384 we have just found out, all right. So, that it will be 9.89. centimeters. All right. Now we write the Green-Ampt equation. All right. We have determined various parameters and variables that are involved in this. Okay. So, f at any time t by Green-Ampt equation is given as kt plus psi delta theta times natural log of 1 plus capital F over psi delta theta. Okay. In this equation, as you see, what are the knowns and what are the unknowns? Well, capital F is what we are trying to find out. Okay. So, this appears on the left hand side and also on the right hand side, both on the left and right hand side. K is the hydraulic conductivity, which is known. T is the time we are going to put at every 0.1 hour. All right. So, that is known. Psi delta theta we have just found out above. All right. So, this is also known. So, everything is known in this equation except capital F. All right. So, we put the values, we generate certain expression, and then we will carry out the manual trials. Okay. So, let us see how we do that. So, we will have f of t is equal to k is 0.05, all right, and t is the time. So, let me put t here, plus you have 9.89 natural log of 1 plus capital F over 9.89. Okay. This is my equation, or this is your general equation which you are going to use. All right. How do we carry out the trial and error procedure? Well, what we will do is we will start, or any iterative procedure starts with an initial guess, all right, or initial value, or some assumption is made. Okay. So, we will just assume some value of infiltration f, all right, and we will put that in this equation. All right. So, we have the left hand side f. What we will do is we will put that arbitrary value of f on the right hand side and evaluate this whole expression. Okay. If the two comes out to be equal, we are fine. If not, we make slight readjustments in the assumed value of f. Okay. All right. So, let us see how we are going to work on that. Well, before we move, at t is equal to 0 hours, all right, to get started, your small f is 0. Initially, there is no infiltration, and small f is infinity. Okay. Initially, there is a lot of these things. All right. So, this is the trivial case, and then we look at the next case at t is equal to 0.1 hour. Okay. Once we put the value of t as 0.1 hour, our equation will become f is equal to 0.05 times 0.1. So, it will be 0.2005, okay, plus 9.89 is your psi delta theta natural log of 1 plus capital F over 989. Okay. So, this is the equation you are going to use or balance out. Okay. It is always a good practice to arrange all your trial and error iterations in a tabular form. All right. If you start writing the things, then it will become very cumbersome and very long. All right. So, what we are going to do is arrange the trial and error procedure. This will be very helpful for all of you during your examinations and quizzes, etc. in tabular form. Okay. That is to say, you will have the serial number, all right, which will start from, let us say, 1, 2, 3, 4, 5, 6 and so on. All right. This will depend upon how many trials you need. Then you have the left hand side, okay, and then you are going to calculate the right hand side. All right. And then depending upon the relative magnitudes of left hand side and right hand side, you will judiciously keep changing your guess for f. Okay. So, let us get started with initial value as 0.0, okay, to get started. All right, you could use any other value also. So, once we put capital F is equal to 0 on the right hand side, all right, for this guy here, right, and calculate everything, the right hand side will be 0.005. Okay. So, right hand side is higher than the left hand side. Okay. So, what we need to do is we need to change the value of our initial gas, all right, and it should be easy to see that the infiltration will have some value, all right. Although we started with 0.0, you could start with 0.1 or any other value, all right. So, what we need to do is I will use certain notation which will be helpful, all right. So, that you need to increase the value of f, okay. This arrow up which is pointing upwards means that you need to increase the value, okay. So, let us say that next time I use the value is 1.0 centimeters. If you do that, this is your left hand side 1.0 and you put the value of f on the right hand side, the value that will come out is 0.9576. Okay. So, now you see that the right hand side is smaller. Earlier the right hand side was higher than the left hand side, all right. So, we increase the value. Now, you notice that the right hand side is smaller than the left hand side. So, what do? We need to decrease the value, all right. So, you see that there is a pattern. So, this is our knowledge we will use in which direction we need to go. Okay. So, now I will put an arrow which is pointing downwards. So, whatever the value of f we had assumed was not right. Okay. So, we decrease it, all right. So, let me go to 0.5, okay, and then put this value of 0.5 on the right hand side and then see what do you get. It will be 0.4928. Okay. Now, can you tell me what do I need to do? The right hand side is slightly smaller than the left hand side, and if that is the case, what we had done in the first trial. So, if you do that, we need to increase the value or decrease the value, and let us say you have 0.1. Okay. So, if your right hand side is smaller, then you need to decrease it. So, with 0.1 you put the value, I will just do this quickly, you will have 1045. Okay. So, you need to increase it, then you have let us say 0.2, it will be 0.2502, and then you need to increase it further. Okay. It should be easy to see, and then finally, if you keep it as 0.3, then you will have the right hand side as 0.320 and 54. Okay. So, you see that we can keep on doing these iterations and then we can achieve certain level of accuracy, all right, that is desired, all right. So, here you see that the guess was 0.3 and which is the left hand side, and the answer which has come out on the right hand side is 30054. So, we say that this is sufficiently accurate. So, we can stop here, otherwise you can keep on carrying out these iterations. Okay. So, if you did that, then you say your final answer capital F is equal to 0.30 centimeters at t is equal to 0.10 hours. Okay. So, what we have done is actually we have found out the value of cumulative infiltration at t is equal to 0.1 hour, all right. Now, what we need to do is we need to determine the value of small f. Okay. What is that? There is a relation as per the Green-Empt equation which is given by this. Okay. All right. So, capital F we have just found out, psi delta theta we had already found out, k is known. So, we can find out what is small f. Okay. So, at 0.1 hours we will have your f equal to 0.05 times 9.89 divided by 0.30 plus 1. Okay. Once you solve it, you have f approximately 1.69 0.954 centimeter per hour. Okay. So, therefore, at t is equal to 0.1 hours, you have capital F as 0.30 centimeters and small f as 1.6954 centimeters per hour. Okay. So, these are the values at t is equal to 0.1 hour. So, you can see that we can continue in this fashion and find out the capital F and small f at other different times. Okay. This should be very easy to see that you can solve this problem using Excel, or you can write your own small computer program in which you can carry out these iterations, or you can use some other iterative method. And Newton-Raphson method is one of the very important and very quick way of determining the roots of an nonlinear equation. So, here we can find out the value of capital F using the Newton-Raphson method if you would like. Okay. The one more example I would like to just take or discuss. I may not have time actually to complete it, but I would like to just give it to you so that you can look at how we are going to, or how you can solve it. So, I will just give you the problem statement for this, and then you see if you are able to solve it. Okay. It is about the application of the Reynolds transport theorem. So, you have a case of a piston which moves vertically downwards with a constant velocity of 1 meter per second. Okay. I will give you the figure in a second. What we have to do is find out what is the velocity of the oil coming out. Okay. Take the stationary CV that is shown. Okay. I will give you the figure in a second, and the density of oil, raw oil, is given to you as 1200 kg per meter cube. So, this is the problem. All right. So, if you look at the schematic of this problem, you have a cylindrical vessel, okay, in which there is a piston that is moving vertically downwards. So, this is your piston. All right. The dimensions that are given to you are that this is diameter is 1 meter of the cylinder, and the piston is let me write it here, inside it is 0.9 meters. Okay. The diameter of the piston is 0.9, the diameter of the cylinder is 1 meter, and there is oil in this. Okay. And when this is moving down, the piston is moving down, what it is causing is that there is oil that will come out with the velocity of v. Okay. So, what you do is you take the control volume right next to the cylinder, okay, like this. Okay. So, this is your CV that is shown to you. Okay. So, what you do is you apply the continuity equation, all right, in which you will have the control surface will be this ring, all right, this annular area from where the water will be coming out. So, you are looking vertically into this. So, this is the annular ring from where this this velocity v, the oil is coming out with certain velocity. Okay. I will not solve this problem, as I said, this is like a homework for you. You work on this problem, all right. It is slightly complicated, and if you have any questions, you can write to me at the email address, or you can contact me. Okay. So, you take this as a homework assignment, and I would like to stop at this point. Basically, what we have done today is looked at these 3 problems which we have solved, and the 4th one is something for you as a challenging problem. Okay. In the next class, we will start a new chapter on atmospheric hydrology, in which we will look at how the rain is formed and different forms of rainfall, evaporation, and all those things. Okay. So, I would like to stop at this point.